Hey guys, welcome to a new unit on gases. In part 1 of this unit, we're going to be talking about different properties of gases, including volume and pressure and temperature. Let's get started. Alright, there are 4 quantities that are needed to define the state of a gas. First of all, the quantity of gas, or N, or the moles, essentially how much gas you have. The more molecules or moles that you have, the more gas that you have. Then we've got the temperature of gas. We need to be using Kelvin for all of these problems, which remember is degrees Celsius plus 273. Then we've got the volume of a gas, and that's going to need to be in liters. We'll talk about why later on. And then finally, the pressure of a gas in atmospheres. So let's talk about those more individually, starting with volume. So a gas uniformly fills any container. It's easily compressed and has a very low density and mixes completely with other gases. So if several gases are placed in a container, each gas occupies the entire volume of a container. So if you have a container that is, let's say, 10 liters large and it's got gas in it, how much volume will the gas take up? Well, the gas is going to take up the entire 10 liters, because you've got random gas molecules filling the container. Now, if you have 2 gases in that container, both gases are going to take up the entire 10 liters. Both gases are going to expand to fill their entire container. So 10 liters of the blue gas plus 10 liters of the red gas makes a total of 10 liters total. So gas pressure is a measure of the force that a gas exerts on the walls of its container. The first barometer used the height of a column of mercury to measure the atmospheric pressure. So here's a barometer, and we've got air pressure pushing down on the mercury. Air pressure pushing down on the mercury. So this is an open tub of mercury. And as it pushes down on the mercury is then going to go up this tube, because where else is it going to go? And so the mercury is going to go up the tube, and the height of the column of mercury, as tall as it is from the pool to as high as it's reaching, is considered the gas pressure. Now above the column, this is a vacuum, which means empty space, not air, completely empty space. And in typical standard pressure, that is at sea level, the height of the column is going to be 76 centimeters, which is the same as 760 millimeters, and the Hg is for mercury because that's what's in the barometer. Or 760 torr, that's named after Torricelli, but it's the same thing, or 1 atmosphere, or 101.3 kilopascals. Now another way you can measure gas pressure is with a manometer. A manometer is a device used for measuring the pressure of a gas. We've got a closed manometer, that's the one over here on the left. It's a vacuum at the top, which means totally empty space, not air. And it's used to measure the pressures below atmospheric pressure. So you'll have some sort of opening on your container that has a stopper in it, and you can put gas in your container, and as you put gas in your container, and then seal it off again. So let's seal off this container and seal off the opening, and that gas is then going to put pressure on the mercury, which is then going to push the mercury up the tube. The difference in height from where the mercury stops to where the mercury ends is your pressure. The difference in height is what's considered the pressure. We also have an open manometer. So this one's open to the atmosphere, so the atmosphere is pushing down, and the gas itself is pushing down, and so we're going to compare how much the atmosphere is pushing to the gas inside the container. So this is used to measure pressure equal to or greater than atmospheric pressure, because we don't want to measure pressures less than atmospheric pressure, because we don't want this mercury to come up and then escape out into the air or like bubble over the side. That seems like that would be a bad idea. But again, the difference in height in the 2 columns is the pressure, considered the pressure of the gas. So pressure is just force per unit area, how much force you're taking up, and how much space. Then we have temperature. Temperature is a measure of the average kinetic energy of atoms and molecules in a system. Hopefully you know that by now. Kelvin temperature is directly proportional to kinetic energy, so if kinetic energy doubles, then Kelvin temperature will double. Not Celsius temperature. Celsius temperature is not directly proportional. They do go the same way. Kelvin or Celsius temperature increases, kinetic energy will increase, but not on a 1-to-1 ratio. Another thing we've seen before is the Maxwell-Boltzmann distribution. Notice that at higher temperatures, such as 1,000 Kelvin, the kinetic energies become more dispersed. So this green line is a little bit lower than the other lines. So the energies could be here or there or there. They could have a whole lot of different types of energy. But the average of all of their kinetic energies is higher at the higher temperature than it is at lower temperatures. So let's say the average is marked by this line right here, which comes at a higher line on this axis of kinetic energy. So if you have a lower temperature, say 250 Kelvin, the average comes at a lower line on this axis. Let's see if I can make that prettier from here to there. At any given temperature, particles with less kinetic energy exert a lower pressure, and particles with more kinetic energy exert a higher pressure. But remember, the total pressure, just like the temperature exerted by gas particles, is an average. So not every single gas particle will exert 1 atmosphere of pressure, but the average of all the gas particles in the container will exert 1 atmosphere of pressure. Same with the temperature. The average is 1,000 Kelvin, but not every single molecule will have that much energy or that much temperature. All right, that's all we've got for this time. This is just properties of gases. We'll see you again next time for gas laws.